Hello, chemistry students. In our last video, we talked about different classifications of matter. And the first level of classification was to separate between a pure substance and a mixture. In this video, we're going to focus on how to separate out those components in a mixture. There's a handful of ways to do this, and in the event that we were to be in class, which we're not because of the pandemic, we'd have a chance to play a little bit with the different types of separating. But we're going to go ahead and talk about how to separate and how each method of separation is unique. Okay, so there are first thing question is, what's the difference between a compound and a mixture? And I usually ask this question in class and say, because we just did compounds and mixtures, what's the difference? They both have multiple substances involved, but what's the difference? What's the big difference between a compound and a mixture? Did you say that compounds are chemically combined and mixtures are not? That's the difference. Mixtures can be separated through non-chemical means, but compounds have to be separated through chemical means. So in this video, we're going to talk a little bit about those methods of separating out those compounds, separating out those materials that are in a mixture into their separate portions. So here are a list of 10 different separation techniques, some of which you probably have a decent familiarity with, some of which maybe not. And we're going to go through each one of these one at a time and talk about, I want you to focus on the following. Under what circumstances would it be appropriate to use that form of separation? What phases the materials have to be in order to use that particular type of separation technique? So that in the event that you had a mixture, you could say, decanting would work here, or crystallization would work here, or centrifuging would work here, and why does that make a difference? Each one of these has unique combinations. So let's go through these in, I think they're in the order they're on the screen. So magnetic, using magnets. Pretty straightforward. Magnets can be used to separate out magnetic materials. Did you know all metals are not magnetic? Not all metals are magnetic. Only iron, nickel, and cobalt are magnetic. So in the event that you want to separate out materials and one of the materials was magnetic and the other ones were not, then you could just simply use a magnet in order to attract the material containing the iron, the nickel, or the cobalt. Okay. So if I had a combination of sulfur and iron filings and I mix them together, not chemically react them together, I mix them together, I could just take a magnet, stick it in there, and pull out the iron filings. That would work perfectly fine. That's pretty easy. And again, very, very specific. One of the materials has to be magnetic. Second one, filtering. Suppose you have a mixture and the mixture contains a liquid and a solid. A liquid and a solid. Well, if you knew the size of the particles, you could choose an appropriate porous filter, some piece of either filter paper or maybe even a piece of mesh or a t-shirt somehow, so that you can separate out the particles by passing the mixture that allows the liquid to go through and then the solids to stay in the filter. That's when you would use filtering. So you want to make sure that the pores are smaller than the particles that you want to collect. That's all. You're looking at a liquid gas combination, so that the liquid is able to go through. This also works if suppose you were trying to run, let's say, a smog. When I used to work in the environmental laboratory, we would get air samples, and one of the first things we'd have to do with the air samples was to run it through a very, 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 very fine filter so that the air that we needed could go through, but we could catch all the particles, dust and debris that might be floating around the air, because we don't want to analyze for that soil part. So usually whenever you have a solid mixed in with a liquid or a gas, then what's going to happen is you're going to choose a filter paper that is small enough to collect the filter. So here's a image. Not sure whether it's going to work. Oh, so you have the materials in the container, and when you mix them together, the greens dissolve into the water and the pinks do not. So mix, 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 stir, stir, stir. The greens mix into the water. The pinks do not. You pour it through the filter paper. The pinks stay in the filter paper, but the greens go with the water into the container below. That's filtering. Okay, not to be confused with filtering, but very, very similar to filtering is decanting. Decanting is when the solid is so large that it is able to condense and fall to the bottom of the container. So if I mix, say, soil and water, I'll use that soil and water as an example. I mix, stir, and allow it to settle. The dirt, and especially if it's really sandy dirt, is going to fall to the bottom of the beaker. Well, then I can just simply decant the liquid off the top. Again, one of the techniques that we used when I was in the lab was this. We would have these mucky, yucky water samples we'd take right out of a lab, right out of a river, and it would be disgusting. And we'd have to allow it to sit for at least 24 hours and then decant off the top layer while still running it through filter paper to take care of any things that did not fall to the bottom. But decanting, all you do is hold a glass rod against the lip of a beaker and pour it straight out. So here you've got an image of the solid brown stuff at the bottom and the liquids on top. If you just pour it with, say, the stirring rod on the lip of the beaker, then it can hold back any small particles of water. Like I said, it's not perfect, but it is a very, very good way to make sure that the material does stay behind. This works really, really well when the solid is so dense that it stays at the bottom of the container, regardless of how agitated you get. That's why we used to have to allow our samples to sit for 24 hours to get them good and solid, so the bottom was very, very heavy, so we didn't have to disturb the flux. The next one is evaporation. Okay, so evaporation is one where suppose you have a liquid that contains solid materials in it. However, it's like say sugar water or salt water. However, you know that if I heat that up, the water is going to evaporate, but the solid is going to stay behind. Here's an example, this little image on the right-hand side, where you have a evaporating dish. It's a small ceramic dish. It's kind of looks like a porcelain pot, and it has salt water in it. And when you run a Bunsen burner underneath of it or some type of hot, then the water evaporates, but the salt stays behind. And when you do that, the evaporation is the technique that you're using to drive it off. Would we use this? Well, very similarly to filtering, this is one where those particles would go straight through. When we saw that earlier example where we had the green materials going straight through the filter and trying to separate out those green particles in that liquid in the bottom, you know what you would use? You'd use evaporation. You would go ahead and drive off that water so that you could take the water that grabbed the green liquid, green particles, and drive that off so you could have just the green materials. And you would have then the pink materials and the green materials. Next is a centrifuge. Centrifuge is one where you take materials that have slightly different densities and you exaggerate the effects of gravity and you spin it around in a device, as these things are across the bottom, they're called centrifuges. You spin it around so that the heavier particles will be pushed to the bottom of the test tube or the bottom of the centrifuge tube, and essentially where you would allow density to do its job by just letting it sit for 24 hours or sit for a period of time, this just speeds that up and separates it out. Again, you have to have differences in densities. This is usually used when time is critical, or maybe when the densities are so close together that you have to exaggerate you have to exaggerate the gravitational force such that they will separate out. Next one is one of my favorite ones because for the first 9.5 years of my chemist life, I was a chromatographer. I did chromatography. Chromatography is really, really cool. What happens is you take a mixture that is really, really difficult to separate, and you have to start analyzing or thinking about what are the compounds that are in here, and how can I make them separate from one another based on one really, really important component, and that's called the affinity of molecule for something else. Affinity is attraction. Okay, affinity is an attraction for something else. So in the lab, when I did this, we would have this really, really long tube and we would pack it with this solid material. But before we packed it with this solid material, it was called a diatomaceous earth, really, really fine sand, we would coat the diatomaceous earth, the very, very, very fine sand, with a chemical we knew some chemical properties of. And we knew the one big thing about that chemical that was in the tube was some of the compounds that we wanted to put into the tube and have run straight through the tube would be very attracted to the sand, while some of the compounds would not be attracted at all. So essentially, a good example, a way to describe this, is the honeybee example. If I had a big pasture of flowers, okay, and I were to release on one side of the pasture of flowers a mixture of honeybees and hornets, a big, big, big swarm of honeybees and hornets. Well, the hornets don't care at all about the flowers, but the honeybees, they do. So what would happen over time as you saw it go across the big thing is that the big field is that the bees would just book across literally a beeline to the other side of the flowers, but the hornets would go in a straight line and never stop along the way. Whereas the honeybees would stop and stop and stop and stop and stop and stop, and they would be delayed in how long it takes them to get across the bed. That's the same idea with chromatography. You've got two materials, one of which is more attracted to what's called the stationary phase. The part that's stuck, in this case the flower bed, is the stationary phase. One of the compounds is more attracted to the stationary phase, and it's going to be pushed across because there's going to be some medium, some fluid, whether that fluid be gas or the fluid be liquid, pushing it through. But the more it's attracted to the stationary medium, the slower it's going to take to go through there. Here's what I did. So what we had was the long tube, and the long tube had that diatomaceous earth in it, and we would inject a sample that was a mixture, and we would use a really small syringe and inject it. And going through this diatomaceous earth, it was very, very hot, usually over 500 degrees. We varied the temperature, so it helps speed things up. So that's a whole other part of chromatography. But we injected into this thing so the stuff stayed in this gaseous form, and on one end, this left-hand side, we would have a constant flow of an inert gas like nitrogen or hydrogen, something that was not going to interact with anything. And all it was a medium to carry the molecules across. Well, as it went across, you can see here the blue molecules are a little more attracted to the material. The pink molecules are more attracted than the yellow, but not as attracted as the blue. And in the end, what we would see is literally waves of compounds coming out, or we call them in terms of peaks. There was a peak, and there was a peak, and there was a peak. And the cool thing, and again, not to make this too complicated, is we could tell what the compound was based on how long it took to get through that tube. We would be able to calculate what that compound was, determine what that compound was based on how long it took to get through the tube. We would do that by taking known substances and measure the time it took to get through the tube for them. So say we put on DDT, a compound that you may have heard about in former biology or life science classes that we used to be used as pesticides in the old days. You put DDT in there. Well, if we knew that we put DDT in there and we let it run and it took 22.2 minutes to go through, and then we would put a mixture in there and there would be another peak that would come out at 22.2 minutes, we could say with some apprehension that substance mixture contained DDT. What we then would do is use a different column with a different affinity and do the same thing. And the more columns we had a confirmation of that time, the more sure we were that the compound that was in the mixture was DDT. Our EPA required us to have at least two different columns of two different polarities to determine whether or not something was actually a known compound. And still we weren't 100% sure. We just knew that we had a confirmation of the times. Anyway, that's a lot of time on chromatography, but it's kind of cool. The next one is distillation. Okay, distillation, what you're going to do there is you're going to exploit different boiling points. If you have a mixture of, say, alcohol and water, an alcohol-water mixture, both of which are liquids, both of which look pretty much the same. But the big difference is that alcohol has a boiling point somewhere around, we'll just use the numbers around 80 degrees, and water has a boiling point of 100. So if I were to warm up this mixture of alcohol and water to say 90 degrees, the alcohol would evaporate off and the water would not. We would separate the two pieces out by boiling points. They're two liquids that are dissolved together very, very thoroughly. But the biggest difference between the two substances, those two liquids, is they have to have much, it's more significant the easier, but they have to have a difference in boiling points. So whichever one is more volatile, has the lower boiling point, is going to evaporate off first so that we can collect it and then be done with it. So here's a typical example of what's called a distillation apparatus. You can see that in the left-hand side over here in this round circle flask, there is the mixture, okay? And you heat it up, and in our example, that was a mixture of alcohol and water. We would heat that up so that the thermostat, the thermometer read 90 degrees. At which point the alcohol would turn into a gas, would go up this tube, would come down here, and this thing over here is called a condensing tube. And the condensing tube just has water running through it, so it cools it down. So it takes it back down to room temperature so it can go back to being a liquid. That's an evaporation flask. So you're going ahead and you're evaporating off the material from one material based solely on two liquids that have two different, that are so thoroughly mixed that you can't separate them out physically without using temperature to separate them out. Next example is crystallization. It's kind of a backwards of evaporation. If you know that materials have different solubilities based on their temperature, for instance, salt has a very, very high solubility even in very, very cold water, whereas a compound, say like aspirin has a very low solubility in cold water. So if I had a mixture of salt and aspirin and I wanted to separate them out, I could grind that stuff up really, 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 really fine, dissolve it in some room temperature water, dissolve. It would collect consistently throughout. And then when I put it into some ice water bath, the particles that are less soluble, in this case the aspirin, would fall to the bottom. They would crystallize out. That's called crystallization. You're turning it back from a dissolved component into a solid form based solely on its temperature and the fact that it has a lower solubility than the other materials. So whereas condensation is used, or distillation is used to separate compounds out with different boiling points, crystallization is used when compounds are dissolved and have different solubilities at different temperatures. One that you're probably fairly familiar with is sifting or sieving. That's just where you can take dry materials and separate them out. So one of the things we use in the lab when I keep going back to my environmental chemist days because I think a lot of the separation techniques were very viable there, was we would take and we would separate out soil. We would take soil in a series of sieves, and big holes, then medium holes, then tiny holes, and then super tiny holes, and we would shake it throughout. And the top sieve, which has the biggest holes, would hold the biggest pieces of material, and the medium-sized holes would hold the ones with the medium-sized material, and the tiniest of materials would go all the way through to the bottom because they fit through all the holes. That's sieving or sifting. It's used when you have a dry material. We would use it on soils and trying to separate the rocks out from the dirt. We really just wanted to analyze the dirt, the soil itself. And it goes through a series of different size holes based on how big the material is. It tells you how far down the ladder they're going to go. And then one of the last things, hand separation. Sometimes you can just pick things up. You can physically just see things. If you can see them and they're large enough for you to grab clearly, then you just pick them up. That's it. There's nothing fancy to it. Sometimes you can just pick through the materials. That's a hand separation. I know it's super, super simple and super, super common sense, but it is a separation technique. Okay. So yeah, that's separating parts of a salad. Or some of you guys who don't like certain foods, like I know that one of my daughters really did not like mushrooms, so she would pull out her mushrooms if I put mushrooms in a spaghetti sauce. That's a hand separation. No chemical reaction taking place there. Okay, so that's the video for this week. Hopefully everybody stays happy, healthy, safe, and practicing that social distancing. We'll be back with another video a little later on, revolving around phase changes. Have a great day. See you next time. Toodles.